All right, so now we're going to take a look at how we classify matter. So when we talked about what chemistry was early on, we said that it was a study of matter. Now we're going to take a look at how we can classify it according to a couple different classification schemes. So generally, when we look at matter, so remember now, matter is just the sort of the stuff of the universe. Anything that has mass and takes up space. We can classify this very broadly at the beginning into two categories. We can have either pure substances akin to just quote unquote chemicals that we talked about early on, or mixtures. And there's some big differences between these two general categories. And in this section, we're going to focus more on mixtures. We'll spend the next few chapters talking about pure substances. So we'll just look at some general differences now. A pure substance or just a substance is a form of matter that has a definite composition, meaning definite here meaning fixed composition and properties. So examples of pure substances would be things like salt, which is just sodium chloride, a sample of iron, for example, or copper. The water that you drink would be an example of a pure substance. And under this category, there are also subcategories that we'll see later on, such as elements, such as iron, for example, or copper, oxygen would be examples of those. And the other subcategory of pure substances would be things like compounds. And these are terms that we're going to define a little bit later on. So something like water, for example, or glucose, which is a type of sugar. These would be compounds, which are also pure substances, right? So the composition of water, for example, is constant, 2 hydrogens and 1 oxygen always. Similarly, for glucose, its composition is the same. So those are pure substances, and these would differ from one another in their composition, and you can identify them by their smell or taste, color, etc. Mixtures, on the other hand, are where we have multiple pure substances that are just physically combined. Okay, so we have more than one substance, we can say that share the same physical space. So in a container, for example, we that physical space. Key thing here is they're not chemically combined, which means that we can separate them fairly easily using normal physical methods. And under the category of mixtures, we have, again, two broad subcategories. We have homogeneous mixtures or homogeneous, and we have heterogeneous mixtures. And the differences here tend to do with the uniformity or the uniformness, I guess, of the solution. Homogeneous of the mixture, sorry. The homogeneous mixture is also known as a solution. Even though we don't use that term a lot, we'll see it a little bit later on. And the homogeneous mixture, again, made up of multiple pure substances, looks uniform throughout. Okay, so one part of the mixture of a homogeneous mixture would look almost identical to another part of it. Whereas in a heterogeneous mixture, it's not uniform throughout. So a mixture that would be not uniform throughout would be something like, if you think about some trail mix, okay, that has, raisins and M&Ms, maybe some nuts. One part of it's going to have more raisins than the other part, right? Maybe spaghetti and meatballs, right? You take a little bit of it, one section of it maybe have more meatballs than the other. And that's different than a homogeneous mixture or a solution that's uniform throughout, something like seawater or just apple juice, looks the same, whether you look at the top of it or the bottom of it, top of the glass, the bottom of the glass that has these things in it, it's going to look uniform throughout. So that's the main difference between homogeneous, heterogeneous, the main difference between mixtures and pure substances. The other way that we can classify matter is based, so we looked here at the composition. So classification based on composition, what they're made up of. The other way we can classify matter is based on the particles themselves. So classification based on particles, the things that constitute that sample of matter, and based on their arrangement, how they are relative to other particles in that sample, and also their movement. Are they free to move around? Are they locked in place, etc.? And based on this, we have three categories that we're going to encounter. We have what are known as solids, okay, and there are different properties of solids than the other two. Solids, particles are close together, very close together. They can't get closer together than they are in a solid. And the particles also have, they can't move around. Okay, so they cannot move around the sample. So they're locked in place, in other words. And typically the particles have some sort of an order associated with them. Okay, so if I have an example, let's say a container here with a solid, if you imagine the solid particles being a sphere, okay, they are packed very close together. You can't really get them any closer. And because they're so close, they can't really move around, right? So they're stuck in place. They can maybe vibrate a little bit, but they definitely can't move around the sample. As a result of this, your solids then have a definite or unchanging or fixed would be another term for that. Fixed shape and volume. Okay, if you think about a nugget of, let's say, iron, okay, the shape of it stays the same. If you pour it from, if you take it from one place to the next, you put it in a container versus on a table, the shape stays the same. The volume that it occupies also is the same as well. It's constant. So solids are different from the next category of matter, which are known as liquids. And in a liquid, the particles are close, but they're not as close together as in a solid. And the key thing about a liquid is that the particles are free to move around. Typically what they do, the particles slide past each other. And they're not locked in place. So if you think of, having a container with let's say a liquid, for example, water is in here, the water particles would kind of be like this. Okay, so they're fairly close to each other. They're not super close as in a solid. There's a little bit more freedom of motion. These particles can move around, slide past each other very easily. And as a result, the shape of a liquid depends on the container. Okay, so the liquid adopts the shape of the container to the extent that it fills the container. But the volume of the liquid stays the same, stays fixed. Right? So if you take a bottle of water and you pour it into a big tub, imagine that there's no holes in the tub. The shape of the water goes from the shape of the bottle to the shape of the tub, but the volume stays the same as well. And the reason why the shape changes is because the particles are free to move around. And that brings us then to the third category, which are the gases. And in the gas sample, the particles are far apart from each other. They're actually very far apart. And they're constantly moving around that sample. And there's no fixed shape or volume associated with it. What we mean by that is that the volume of a gas would be dependent upon the container that it's in. So the gases adopt the shape and volume of the container that they're held in. Okay, so your book does a fairly good job of showing you the differences between them. So if I had, just to continue my descriptions here, so if I have a gas sample, particles are spread out in this container, they're zipping around, right, with a great deal of speed. Always in constant motion, a lot of space between the gas particles themselves. And if you're ever confused, about these three different physical states, you always want to think about the one material that actually does exist in all three states, solids, liquids, and gases at normal temperatures, and that would be H2O, water. So water does exist as a solid, right, which we call ice. It exists as a liquid, which we normally refer to as just water. And then it also exists as a gas, right, water vapor. And it does exist fairly easily just by changing the conditions, adding more heat. We can melt ice into water, liquid water. And if you add more heat, we can vaporize the liquid water into a gas. By vaporization, right? But under all of these three different examples, it's still, the identity stays the same in all of these. Still H2O. All right, and then we'll take a look at some of the properties of matter. And again, we saw the term properties before. Property is, in chemistry, is just another term for the word characteristics. Okay, and again, we can classify properties a couple different ways. We've seen a couple of these terms before. There are two general types of properties initially. We have what are known as quantitative properties, okay, where these are characteristics or things that are measured. And in a quantitative property, we're going to be using some sort of a measuring device. And make a measurement, right? We have to have a number and a unit associated with it. So quantitative properties are things that can be measured. So for example, the mass of an object or the volume that object occupies, etc. These are things that can be measured using an appropriate device. This is in contrast to qualitative properties or qualitative characteristics that don't require measurement, right? We don't need a device to observe these qualitative properties. Instead, what we need to rely on are observations, right? Using our senses, sight, smell, touch, etc. So for example, something like the color of a substance or the texture, the way that it feels, to the touch. Those would be examples of qualitative properties. So quantitative versus qualitative. And again, we've seen these two terms before. Other types of properties that we can differentiate that we see quite commonly are physical properties. And then we also have chemical properties. And we'll look at it both from the perspective of properties or characteristics and also changes that accompany or that kind of flow along with those. So a physical property, a physical characteristic is one that we can observe, right, using our senses, using different devices or measured without actually changing what that substance is, okay, without changing the identity of a substance. So for example, if I report the color of a piece of metal, I can make that observation without trying to change the metal into something else. I can measure the melting point of ice. Right, when I make that measurement, I don't change the identity of that substance. It still is H2O when it goes from solid ice to liquid water. And similarly, if I measure the boiling point, right, I can make that measurement without trying to change the identity from H2O to something else. So those are physical properties. And a physical change, kind of flowing along with that, is a change whereby the state of the matter changes. Okay, so the state of matter would be something like solid versus a liquid versus a gas, but the identity of the matter does not change, right? So the key thing here with physical properties and physical changes is that the identity of the substance stays the same. So for example, when ice, for instance, melts, right, it goes from a solid to a liquid, right? That's the melting process. And that's a physical change, right? The substance actually changes, but it doesn't change chemically, it changes physically. The state of matter actually changes. If I take a piece of paper and I tear it in half, now I have two halves of this piece of paper, right? It still is paper. All I've done is change it from being one entire sheet to two sheets. That would be a physical change as well, right? The identity has not changed. It's just how it's put together is what makes it different. All right, so in contrast to physical properties and physical changes, we have chemical properties and chemical changes. And in a chemical property, that is one that a substance is going to show as it interacts with another substance and as it undergoes a chemical change. So the physical property of something like corrosiveness, right? So let's say iron possesses that property because as it exhibits that characteristic, it interacts with other substances like water, like oxygen in the air, and it changes into something else, or changes into rust, for example. So that property of corrosiveness would be an example of a chemical characteristic or a chemical property. And then a chemical change is a change that does result in the change of composition. The original substance then is no longer going to exist. You can say there's a change in the identity. Okay, so for example, a chemical change, a good example of chemical change would be the digestion of the foods that you eat, right? So for example, as food undergoes digestion, as you probably know from experience, it's not food at the end, right? It changes into other things. Right? So it gets broken down into carbon dioxide, gets broken down into other, and you exhale that, and as a result of that process, a bunch of energy is generated. So this would be an example of a chemical change. Similarly, in the example we looked at before, if you have something like iron, okay, and it undergoes oxidation, it can become rust. Okay, that's a chemical change going from iron into rust. The rust at the end that we end up with is not the same thing as the iron that you started with. It's very different, right? The composition has changed. So we have chemical properties, chemical changes, and those are in stark contrast to physical properties and physical changes. The last set of properties that we'll take a look at are extensive versus intensive properties or characteristics. An extensive, and sometimes you might see the phrase or the term extrinsic. Maybe you don't see it as much, but sometimes it's thrown in, and depending on where you look. Extensive properties or characteristics that do depend on the amount of the matter that you have. So an example of that would be, the mass or the volume, right? So something, a substance that has that's bigger, for example, if it's the same substance but a different size, it's going to have a bigger mass, it's going to occupy a bigger volume. So the mass, for example, would be an extensive property. The amount of matter in it changes dependent upon the size of the sample. That's in contrast to an intensive property that does not depend on the amount of matter that you have. All it depends on is just what that substance is. So just the identity of the substance. If it's the same substance, doesn't matter the amount, this property is going to be the same. So for example, if you look at the density of, let's say the density of gold, okay, whether you have an ounce of gold or whether you have a ton of gold, the density is going to be the same. It does not depend on how much of the matter you have, and the reason for this is because, remember now, density is just a ratio of the mass to the volume. So if you increase the mass, the volume that it occupies is going to increase by the same proportion, so that when you divide them, you end up with the same value for the density. So intensive properties does not depend or do not depend on the amount of substance that you have, whereas extensive properties